Okay, so we are going to study the first topic on what is magnetic flux. So let's move on to the first topic. So what is magnetic flux? Magnetic flux is described by a symbol of phi. This is a Greek letter small phi. Okay, and the unit for magnetic flux is Weber, which is represented in the symbol as WB. W is capital letter, B is small letter. Okay, I will describe what is magnetic flux a bit later, but for now you need to know that 1 Weber is equivalent to 1 Tesla meter square. Okay, this is Tesla, the unit for magnetic field strength. Then you have meter square, which is representing area. Okay, magnetic flux is a scalar quantity. And now here I'm going to describe what is magnetic flux. So magnetic flux, you can calculate it like this. It's a mathematical quantity. It doesn't carry much meaning, but we scientists discover that if this value change, then you induce an EMF or induce a current. Okay, not or, it's and induce and current. Okay, but this value is just a mathematical value for us to check whether there's changes or not. It doesn't really carry much significant meaning for now. It's not something like feel. It's not something really physical or what. Okay, it's just a mathematical concept. So it's like this. If your magnetic field is uniform over a plane surface with total area A, so it means right, if you have an area with total surface area of A, and across the whole surface you have a uniform magnetic field passing through it, then you can determine the magnetic flux phi by using scalar product of B dot A. Okay, dot product of magnetic field and the area vector. Again, if you have an area of area A and there's a uniform magnetic field passing through the area A over here, then you can determine the magnetic flux through this area here by using a cross product, not cross product, dot product of magnetic field and area vector. So dot product is cos theta, and the theta over here will be the angle between the magnetic field and the area vector. Okay, so we know very well about magnetic field. We have been discussing it since chapter 4. It's just uniform magnetic field. They usually give you a value, or sometimes you're asked to find the value. Okay, so it can be created by a permanent magnet or by an electromagnet, but that is not our concern. Something new in this chapter right now is the idea of area vector. Okay, this area vector here is now pointing downwards, and it's below the page, something like that. Okay, your magnetic field is passing through the page from up to down, and your area vector is pointing downward, something like this. Okay, so area vector is a new concept. Let's try to study how to determine the magnitude of an area vector and how to determine the direction of an area vector. So the magnitude of an area vector is just the area that we usually calculate. So if this is a rectangular shape of area, then you take the length times the width, and you get the area of the area vector, the magnitude of the area vector. Okay. If it's a circle, then it's pi r square. If it's other kind of shapes, then you just find the area of those 2D shapes. So basically, the magnitude of the area vector is just how you usually calculate area. But something new, something extra, something additional to the area vector right now is that now your area also carry direction. Okay, and we have already mathematically defined that the direction of an area will be perpendicular to the plane of an area. Okay, so if today I have a piece of board here, and this board here is representing an area, then there's two direction that is perpendicular to the area over here. So again, this is the plane of your area. This is the plane, the plane of your area. So you want your direction of your area vector to be perpendicular to the area. The plane of the area is like this right now. You want it to be perpendicular to the plane of the area. So now there's two choices of what is perpendicular. One is pointing upwards, something like this. Another one is pointing downwards, something like this. Okay, so no matter what, it should come out from the plane, but it should come out like either pointing downwards or it should come out pointing upwards. So no matter what, it's always 90-degree between the area vector and the plane of the area. Okay, so both directions here are perfectly acceptable. both direction here should be perfectly acceptable, but you arrive with different answer if you pick different direction of area vector. If you pick up, then you might get a positive answer. If you pick down, you might get a negative answer. Or sometimes you pick up, you get a negative answer. You pick down, you get a positive answer. The sign will change depending on the direction of area that you take. So it's perfectly acceptable to pick any of the direction, either in this direction or another direction, but we usually stick to the one that is in the direction of the magnetic field. So if we have magnetic field pointing into the page, if you look from up here, it's pointing into the page. If that is the case, then we usually put our area vector to be pointing downward. If it's pointing into the page right here, then we take our magnetic field to be pointing downwards. If we have our magnetic field to be pointing like this, so if you view from this perspective, if you view from up here, it's pointing out of the page, the magnetic field is pointing out of the page, then you will put your area vector to be pointing upwards like this. You try to follow the direction of the magnetic field. If your magnetic field is at an angle, you try to pick the direction of the area vector that is more that is in the same direction. Okay, if your magnetic field is pointing in this direction, which is at an angle, then when you pick your area, you can choose either this direction or this direction, right? You pick the one that's in the same direction as the magnetic field. You don't pick the one with an angle that is larger than 90 degrees. Okay, it's not that you cannot pick, you can still pick it. You get an opposite sign for your answer, but everything is still perfectly acceptable if you stay consistent with the direction that you pick. So it's always make sure that you pick one direction for area vector and you stick to the area vector direction that you pick. Okay, so that one is very important. Okay, so this is magnetic flux. You just need to know that it's a dot product between the magnetic field and the area vector. Area vector, the magnitude is just a normal calculation of area. The direction, you can free to choose any direction that is perpendicular to the plane of the area, but we usually pick the one that is in the direction of the magnetic field.